All right, 4.4 is polynomial equations, inequalities, applications, and models. So in this section, we're really going to take everything we've talked about and kind of bring it all together. Question A says, solve this cubic polynomial using the zero product property. When you see these words zero product property, what that's telling you to do is factor and set it equal to 0. So we want to write it as it's 3 factors. So if I look at A, I would probably use factor by grouping, noticing that these terms, they have some stuff in common. They have a common factor that I can break them out together. So x to the third and 3x squared, they have an x squared in common. And so when I factor that out, I'm left with an x plus 3. And then the second piece, minus 4x minus 12, they have a minus 4 in common. And when I factor that negative 4 out, I'm left with an x plus 3. So this is nice because they have a common factor, and the leftover thing is x squared minus 4. So if we go back to what we were learning in chapter 3 about squares, this guy is a difference of squares. So I can factor that out even further to x minus 2, x plus 2, and x plus 3. And now I can use the zero product property and say equals 0 to find those x-intercepts. So I have an x-intercept at 2, an x-intercept at negative 2, and an x-intercept at negative 3. So we found those. We have a graph that's already given for you. Let's go ahead and label those x-intercepts. So right here, this is the negative 3. This is the negative 2. And this is the positive 2. And just to think about the analysis of the graph, this y-intercept down here, I'm going to go ahead and put it on there. That's the negative 12 for the y-intercept that came from our standard form of the equation. It's a cubic polynomial. It has 3 real zeros. The number in front of x cubed is positive, so we're going to start down at the bottom, and we're going to go around, and we're going to end going up because the number in front of x cubed is positive. So it's going to end down and then end up on the other side. All right, part C, use the graph from your part B to solve the inequalities. So we are still really struggling with interpreting what this means. When I say a function, this is our function right here, greater than 0. This means above the x-axis. That is asking us for what x values, what domain numbers is the function above the x-axis. Well, above the x-axis is this little piece right here between the negative 2 and the negative 3. And then this little piece right here on the end from 2 to infinity. So this is a greater than symbol. It's not equal to, so we have some parentheses. Negative 3, negative 2. Oops, sorry, negative 2. And from 2 to infinity. And then the other part that they're asking us to do is less than or equal to 0. So if I say the function f of x, whatever it is, in this case it's this cubic, is less than or equal to 0, that means below the x-axis. So we're saying, where's the function below the x-axis? So the function is below the x-axis from negative infinity to negative 3. It's below the x-axis then from negative 2 all the way to positive 2. So those purple pieces that I just traced. So we have negative infinity to negative 3, and this has a bracket because of the equal underneath that less than. And then from negative 2 to positive 2. That is where it is below the x-axis. This concept of greater than less than 0 is very, very important. So we're going to be doing this notation for every function we study. It's important that we understand what that means when I say a function is greater than or less than 0. We're talking about above or below the axis. All right, example 2, solve an equation in quadratic form. So when they mean quadratic form, if I think about these powers, the fourth and the squared, This looks quadratic, like there's no x to the third and x to the first power in it. So it's going to factor the same way we would factor a quadratic. So if I think about what multiplies to make 40 and adds to make 6, I have 1 and 40, I have 2 and 20, not a 3, but a 4 and a 10, and then a 5 and an 8. And I'm looking for which pair can I use to make a 6. If I do 4 minus 10, I can make 6. So this is going to factor into x squared minus 10 and x squared plus 4. Okay, and it says solve it analytically, find all the complex solutions. So if I can break it into two quadratics, this is actually relatively easy to solve. We can actually straight solve each of these quadratic pieces. So if I take this first piece, x squared minus 10, it is a difference of squares, but something that's nice that happens even with our sum, and we have a sum of squares and different squares, is I can directly solve this. I can move the 10 over, x squared equals 10, and now I can square root both sides. So I have x equals plus and minus square root of 10. That is one set of zeros. Now I'm going to do the other set of zeros. This is very helpful with a sum of squares, and we'll actually look at how it's actually related to the difference of squares, because something real similar happens. So if I have x squared plus 4 equals 0, I'm going to move the 4 over. X squared equals negative 4. And now what happens, I'm going to square root both sides, so x equals the plus and minus square root of negative 4. But what is the square root of negative 4? Well, it's an imaginary number, so it's plus and minus 2i. So if I were to write this out factored, let's talk about what this looks like factored. So factored, I can write x minus square root of 10, x plus square root of 10, because it was plus and minus. And then the other one that we came out with the imaginaries, we have x minus 2i, and we have x plus 2i. So that's what it could look like factored form. Whatever we find those zeros, we just say x minus blah, 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 whatever the number. All right, so where are those at on the graph? The only ones we see on the graph are the pink ones. The exact value, this one is the negative square root of 10, and the exact value over here, this is the positive square root of 10. This course, we're going to focus on the exact numbers. This exact number is the only one we care about. You are not going to give me approximate decimal numbers unless it says use the graphing calculator to solve. Otherwise, we are always going to be doing the exact numbers. So let's talk about the inequality piece with this. So again, just like the last one, when I talk about when is it greater than 0, that means above the x-axis. So where is this guy above the x-axis? He's above the x-axis from negative infinity to negative root 10, and from root 10 to infinity, those pieces I just traced green. And this time it says greater than or equal to. So I have negative infinity to negative root 10. Notice I'm using the root 10, not the decimal approximation of 3.16. And then it's also from square root of 10 on the other side to infinity. All right, the other piece we're looking at for when is it less than 0. So we're going to be less than 0, meaning below the x-axis, this wavy piece at the bottom under the x-axis. We are less than 0 between our two intercepts. So from negative square root of 10 to positive square root of 10. All right, solve polynomial equations analytically. So we're going to look at the different strategies that we've used from examples 1 and 2 and figure out which one we can use to solve A. So if I look at example A, I need to think to myself, does that look more like example 1, where I could factor by grouping things together and pull out a common term? Or does that look like it's going to behave like a quadratic, meaning there's no odd terms in there, or odd powers? So if I look at A, notice the powers are even, so that's going to behave like a quadratic. So if I try to factor this guy, I need to think about what AC is, because it's going to behave just like a quadratic, 36. I'm looking at which factor pair of 36 can make a 5. So 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6. So 4 and 9 will make a 5 if their 9 is negative. So let's think about what's going to happen here. I have 4x to the 4th. If I'm clever, I would group the 4 with the other 4. So minus 4x squared. Oh, nope, that's a plus. Minus 9x squared minus 9. So now if I factor these by grouping, I'm going to group these first two terms. They have a 4x squared in common. And that's going to leave me with an x squared plus 1. And then if I group these other two terms together, they have a minus 9 in common. And when I pull the minus 9 out, I'm left with x squared plus 1 again. So now writing these in the two factors, 4x squared minus 9 and x squared plus 1. And we see something happening that's pretty similar to the other one. So we have some ideas here. We can identify this 4x squared minus 9 as a difference of squares, and we can go ahead and factor it, or we can directly solve. Both methods work just fine. If you recognize this as a difference of squares, you might write it as 2x minus 3 and 2x plus 3. You might be able to identify the x squared plus 1 is going to have an imaginary solution. So we're to write it kind of like we'd write x squared minus 1. The only thing is going to be x minus I and x plus I. So let's say you didn't recognize that. No big deal. There's another way to approach it. We can approach this like we just did the other problem, and we can directly solve because there's no middle term for each of these. So I could do 4x squared minus 9 equals 0. Move the 9 over. So 4x squared equals 9. Divide the 4 off. So x squared equals 9 fourths. And then square root both sides. So x equals, the square root of 9 is 3, and the square root of 4 is 2. So plus and minus 3 halves, or 1.5. So if there's no middle term, you don't necessarily have to factor. You can directly solve. So that is an option for you if you don't see the factors. It's not a big deal. So if I do the other one that way, x squared plus 1 equals 0, move the 1 over, x squared equals negative 1. And here's where we get that plus and minus I. So x equals plus and minus I. So those are our zeros, our roots, our x-intercepts, the solutions, if you will. Now let's look at B. The issue with B is the way it's written right now. I'm looking for where some cubic intersects some parabola. So the only way we can analytically solve this is to move everything over to one side and solve a related problem. So to do that, I'm going to have to move the 3x squared over and the 8x over. So I'm going to rewrite it 2x to the third minus 3x squared plus minus 8x and then plus 12. So we have some options. Oh, we equal 0. You can rearrange these terms. It's going to work out the same way regardless, so it doesn't really matter too terribly much. I'm kind of on the lazy side, so I'm going to leave them in the order that they are in to group them. These two things, the only thing they have in common is an x squared. So I'm going to be left with 2x minus 3. When I look at these other two terms, the negative 8x and a 12, I think they have a factor of a negative 4 in common. And I did that on purpose because I want this plus 12. I need that to be a minus 3. So instead of just pulling out a 4 that they divide by, if I pull out a negative 4, it's going to change those signs the way I need them to be. So that's going to leave me with a 2x minus 3, which is what I was trying to get, so it matches the previous one. So now I have x squared minus 4 and 2x minus 3 equals 0. So again, we have the same option that we had in the previous one where we can recognize x squared minus 4 as a difference of squares. We can write this fully factored if we want to. X minus 2, x plus 2, and 2x minus 3. We can write it that way, or we can directly solve like we did in the previous problems. X squared minus 4 is a pretty easy one to write in factored form. You might actually look at that and then automatically say x equals plus and minus 2. And the other one we have to solve for 0. So if I move the 3 over, divide by 2, I get x equals 3/2. So that is solving analytically. And then the last example we'll do is show that 2 is a real solution of this polynomial and then find all of the solutions. So this is really powerful when we can look at a graph and we can say, hey, I know this graph has one very nice x-intercept right here at x equals 2. That graph very clearly crosses the x-axis, and you can use the one friendly 0 to find the other two. When I do this, I use synthetic division because it's quicker, it uses less space, there's less room for errors. So if I use synthetic division, I have 1, 3, negative 11, and 2. And keep in mind, if it is a solution, we're going to have that remainder 0 happen. So we're trying to get a remainder 0 in this last box. I'll be left with a quadratic that I can then factor no matter what, even if I have to use a quadratic formula. So if I use synthetic division, 2 times 1 is 2. I'm going to add those. I get 5. 2 times 5 is 10. I'm going to add those. I get a negative 1. Negative 1 times 2 is negative 2. There's my remainder of 0. This right here is the remaining quadratic, x squared plus 5x minus 1. And just by inspection, that is not going to be factor friendly. The only thing I can multiply to get a 1 is 1 times 1, and 1 plus 1 does not make 5 no matter what I do. So we have to use the quadratic formula if it's not factor friendly. I guess we probably could complete the square, but I wouldn't complete the square because 5 is negative, or sorry, 5 is odd, so we would have to like cut 5 in half, square it. I don't like doing that with fractions, so if we use the quadratic formula, we have opposite of b, so negative 5, plus and minus the square root of b squared. So 5 squared is 25, minus 4, a is 1, and c is negative 1, all over 2a, so 2 times 1. So we're to clean this up. Negative 4 times 1 times negative 1 is a positive 4, so 25 plus 4 is 29. This ends up being negative 5 plus and minus the square root of 29 all over 2. So those are our two zeros. They are real because 29 is positive, but they are not friendly numbers. So if we put it in the calculator, we would get these ugly decimals. That is an irrational number. So when we talk about the rational roots, we're talking about the friendly ones, the ones that are just nice fractions. There's not really anything too complicated. So we have one of them right here, and the other one, if we try to do negative 5 plus the square root of 29, let's see what number we get when we do that. I'm going to pull up a Desmos graph. Because I believe, just by inspection, it should be pretty close to 0, because the square root of 25 is 5. So it should be pretty close to 0. Let's turn this off for just a minute. And we said negative 5 plus the square root of 29. Oops, it should be negative 5, not negative 1. And see right there, we're pretty close to 0. And then we're going to say divided by 2 for the whole thing. We get 0.19. So that's why on the graph, when we look at the graph, the picture that was given, we see it pretty close to 0. It's not quite 0, but it is pretty close. If you're not, you might have to zoom in to see that that doesn't actually cross to 0, but it's very, very close to 0. So that is the first part of 4.4.